So, as I mentioned, we are going to begin fatigue. This is an interesting portion of the course. This is something that's fairly unique to mechanical engineers. That you won't see as much study of this topic from most of the other disciplines. It matters to us because one of the things that mechanical engineers are expected to do is evaluate things for suitability in certain types of equipment where there are moving parts, right? Where there's some sort of process that's happening, and often the process that's happening is cyclic in nature. Okay, you think about, for instance, an internal combustion engine. You've got a connecting rod that connects the crankshaft to the piston, all right? As that crankshaft moves around, that connecting rod, during some portions of the cycle, will carry very large amounts of compressive stress. In some parts of the cycle, it may carry tensile stress, and the engine runs at a fairly fast pace, right? So that means that there can be a lot of cycles of load that happen on that connecting rod in a fairly short period of time, okay? So what we're talking about with fatigue is basically this. It says here, when parts are subjected to fluctuating stresses, that's what I was just mentioning, is that you can have situations where parts don't carry just one stress. The stress changes over time, and sometimes it can change rapidly. And it can swing from being compressive to tensile to compressive. And as that changes, the stress changes, what happens inside of the material is that there are a lot of little, I would say micro discontinuities inside of the material. And wherever there's a little micro discontinuity inside of the material, it is likely that there might be a tiny little bit of yielding at a very, very localized microscopic location in that material. Okay? If that happens, then when it yields, it is actually doing a few things. One is it's absorbing energy, right? As it yields, if it yields one direction, then the other direction, one direction, then the other direction, it is actually having to absorb energy, so that's one thing. But the other factor that goes on there is actually a very similar thing to if you've ever played with a clasp on an envelope, and you've taken a clasp and you've bent it over and over and over and over again. It doesn't last forever, right? Okay, so what goes on there is that in that material, any place where there might be a little microscopic discontinuity, it kind of behaves as if it's a little crack right there. And if you start causing there to be yielding in one direction and another at that little micro discontinuity, it actually starts to break more bonds, and the bonds that it breaks might be in surrounding material right around that little discontinuity, and as you keep doing it, all of those little broken bonds that may not have been able to heal back up, due to the ductility of the material or whatever, those little bonds all end up, all those little voids where you don't have the bonds, they tend to start coalescing into these bigger voids. And then after a while, then your part will break. Okay? So what's interesting about this is that those stress levels, so we'll get back into this statement here, when the parts are subjected to fluctuating stresses, the parts are likely to fail at stress levels that are much less than the yielding or ultimate strengths that you would have used to predict when it would fail. And that happens worse and worse and worse as you go to larger and larger and larger numbers of load cycles. Okay? So what's interesting about this is that you don't even have to be observing any sort of macroscopic plastic deformation. This type of an effect happens even when it looks like it's still remaining elastic, and it doesn't look like you're adding any sort of a permanent deformation at any point. You can still have this phenomena of fatigue begin to happen. Okay? And so because we've known about this for a long time, as human beings, at some point there were some tests that people decided to start running to try to figure out how can we start quantifying this effect, because it's still, even to this day, it's not understood perfectly well. Like there's not a perfect model that we have, analytical model, that allows us to quickly know exactly how many cycles at some stress level we will have. And part of that is that because it has to do, the best theories go anyway, it has to do with these little microscopic discontinuities in the material, the mathematical nature of it tends to be much more stochastic rather than deterministic. We usually think of a material as being, completely isotropic, same properties everywhere, same properties in all directions. We think of our materials that way, but in reality, materials have little problems inside of them, and so where those problems are and exactly how they manifest, those little discontinuities, can change from piece to piece. And so it's very difficult for us to predict exactly how things are going to fatigue. Okay? But having said that, we still need to be able to design things. That's actually something that's different about engineering versus some other disciplines like, say, mathematics or something. In mathematics, you have to just sort of give up if you don't have a good model of how to deal with something. In engineering, we still have to make parts. Right? Even if we understand that they could break, people still want products. People still want to be able to drive a car. Right? So you have to be able to continue to design your parts even if you don't fully understand the exact mechanism of how a failure occurs. So toward that end, experiments have been devised where you intentionally subject a piece of material to a cyclic load. Okay? And the most common way of doing this is with a specimen. There's a little picture up here that you see. This specimen is a common shape for a rotating bending test. And so I brought a little, I used this. Several of you have probably been in my office, and we've gotten to use this little rod of material here. It's kind of a rubber, and you get to see the different kinds of stress. I thought I'd bring it in here to describe and help describe how the stress is cyclic in a rotating bending specimen. Okay? So think of it like this. First of all, they take this specimen. You see here there are two forces of F that are applied at a distance of A, and again over on the other side. Right? So what you see happening there, that is going to create a flexure. Okay? And if you think about that, you look at a little element of material up on the top of the specimen, it will be in tension when it's in this orientation. Okay? What happens is the fixture that is doing this test holds it in that position, but then turns it like this. Okay? So as I have now turned that, you think about that piece of material, or that little element of material, it's now down here. Okay? And so what kind of stress is it experiencing now? It's compressive. So if you keep on rotating it another half turn, now that same element of material has gone back to being in tension. And if this thing is rotating at some pace where you have this bending moment happening and that simultaneous rotation, then that little piece of material is experiencing this fully reversed cyclic load. Okay, so that's a term that we will begin to use in here of being fully reversed. Okay, and what we mean by that is it's the same stress magnitude on one end of the range as on the other. It's going to be tension on one end of the range and compression on the other end of the range. Okay, I'll go ahead and mention now there's a few other kinds of cyclic loading that can happen. What if I had a piece of material and I was applying an axial load to it, and so I pulled on this and then I released, and then I pulled on it again and then I released. Okay, what we would call that is it's a repeated load. Right? It means that we are not reversing it. We don't ever put a compressive stress in it. We just keep on pulling and then releasing, pulling and then releasing. And so there's a different sort of nature to how that one will fail. And we're going to get into some theories that allow us to deal with those situations where we don't have maybe a specific type of stress profile. Okay? So that's what we're talking about. This is the rotating bending specimen. And what you see with this little chart that is shown right here, this is a really fundamental chart that we have to deal with to understand the outcome of the rotating bending tests that are done. So what you see on here is these all these little data points. These represent ostensibly identical specimens. Same type of material, same exact dimensions, all right? The only difference being that for each of these specimens, they are loaded to a different amount of load. And so they basically change the Fs that are applied, and then they put them in the machine and run the machine. Okay? And what they plot is basically how many cycles do the specimens take at that particular stress level. So they're able to calculate the stress level based on the dimensions A and the force F, right? And they can essentially plot that stress level as one of the dimensions and then the number of cycles as another dimension. And as they do this, the chart that you're seeing up here is for steel. Okay? As they do this, the shape of this chart for steel winds up being fairly uniform. Okay? It's like we don't necessarily care exactly what kind of steel or exactly what strength level of steel. The more or less the general shape of this curve stays roughly similar as long as you're dealing with steel. And so what we're going to do is apply some thinking about how we can use this chart and be able to predict the behavior of materials that are loaded cyclically. Okay? So that's where we're going to go. A couple of things to point out here, and kind of one of the most obvious pieces that I'll show on here is this range of the chart way out here. Okay, see where I just drew that red line? So this is interesting. This is a feature of steel that exists in very few other materials. Steels have this characteristic that if you let this stress value go low enough, there will be a point at which it doesn't matter how many cycles you put on it. All right? You can essentially run the number of cycles as high as you want to, and it will not have really any additional effect on when the material will fail. In other words, you can go on forever and ever and ever. As long as you hold this stress level below a certain threshold, it can essentially last forever. Okay? Well, that's kind of interesting. What's interesting here is that number you see here for this steel. It looks like that occurs at about 1 million cycles, and that is uniform enough to where we are just going to take that as a universal value. We'll basically say if a steel is going to last 1 million cycles, then we're going to assume it's going to last 1 billion or 1 trillion. Okay, so if we've designed something where it'll last 1 million, we're saying it'll last however many more you want. Okay, there is some debate about this as to whether it happens at the million or at 10 million. Right, but we're in here for just to get the idea of how to do these problems. We're always going to just take that value to be 1 million. And then what you see here, this height of that curve right there, is called the endurance limit. And I'll just go ahead and make the comment here that the endurance limit is a big deal to us because the most common way to do design with steel is to just decide that you are going to try to make your part last forever. Okay, it's uncommon for people to try to make the decision that they want their part to last some number of cycles that's less than infinite if you're designing in steel. You sometimes don't have that luxury if you're designing in some other kind of material, right? You sometimes have to do a more finite design kind of approach. But with steel, we're generally designing out here for this endurance limit. Okay? So then kind of one of our first questions is there a way we can estimate what that endurance limit is? And the answer is kind of multi-pronged. One is, if you have had someone do a fatigue test for your specific kind of material that you're thinking about designing with, right? Well, then one of the things that comes out of that is probably going to be a really good estimate of endurance limit. We're going to add another constraint on ourselves, though, for the types of problems that I'm most interested in you being able to solve. I am going to pull out a constraint that says I want you to be able to design for steels where you only have one piece of data about that steel. and that piece of data is your ultimate strength. Because that's one of the pieces of data that you will have for just about any kind of material that you're going to design with. That's an easy one to have, the material testing data for that. You will always basically have your ultimate tensile strength for your material. And so one of the things that's helpful is there's another chart in the textbook that allows you to make an estimate of what the endurance limit is going to be if you happen to know the ultimate tensile strength. Okay? These are basically a lot of different kinds of material where they did these kinds of tests, and you see what they're doing here is that even though it's not fully deterministic, there is definitely a trend that happens, and kind of the middle of that data is kind of right through there like that. The way we can interpret that, and actually I'll tell you what I'll do here. That line goes up like this. There comes a point where the data starts scattering down here lower. You see that?
Why does some of it go laterally and some of it go
So there's the best explanation for this. I'm not sure that people understand it perfectly well, but probably the best explanation for why it cuts over like that is if you look at the strength of these materials, right? Somewhere at around 200 KSI. That's a really strong steel, all right? That's a pretty high strength value for steel. And so what happens when you get steel to high strength values, it usually means that your steel has gotten more brittle. You usually aren't able to keep your ductility of your material all the way up into those levels. And so the thing is that having more ductility is helpful in terms of being able to withstand, right, because if you don't have ductility, then when your bonds break, they're more likely to just stay out of the game. Okay? So that's probably the best explanation for why it cuts over like that, is that these high levels of strength, they're really, maybe your material isn't quite as capable of sort of self-healing. That's not really an official word or term, but that's sort of how materials behave when they are ductile. So anyway, this chart that you see right here gives rise to the estimate that is used in the book, and they use this SE prime. And basically, I'll just only state it for US units. We say that this is going to be half of the ultimate strength as long as your ultimate strength is less than or equal to 200 KSI. Slide all this over a little bit. Okay. Otherwise, we just cap it off and say we're only going to let it go up to 100 KSI if it's any higher. Okay? So this is our first thing that we look at with respect to this chart, is understand that there is this stress level, and as long as we don't go above that stress level in our designed parts, we can sort of expect that the part will last forever. Okay? There's going to be a little asterisk next to that fairly soon, but I'll go ahead and leave it there for right now. Actually, maybe I'll mention it. The prime that I put on here, the prime means this is if you have a highly polished, rotating bending specimen at room temperature, and there's a few other things as well. It's basically like, do you have the perfect case? So it turns out that when they do these tests, if they do not perfectly polish the surface of this material, it very, very rapidly changes the result. Okay? Why do you think that might be? Yeah, any sort of roughness on the surface is basically the beginning of a crack. And you're creating these little microscopic stress concentrations anywhere where there's roughness. So if you make it perfectly polished, perfectly smooth, then these are the data points that you get. One of the things that we will deal with in the next lecture is what do you do if you have material that's not? Okay, so we will deal with that question at some point. But what we're doing right now is that this is the endurance limit that we expect for a perfectly polished rotating bending specimen. Okay? All right, so the next thing we need to do is identify that the two axes of this chart are on log scales. Okay, so this is an important feature that we have on a chart like this. And it means that the relationship between your variables doesn't really behave just according to straight line equations. It's a straight line, we model this with a straight line on log scales. Okay? And we see that on these log scales, there's a couple of points where it looks like there are some breaks. Now, one of the things I've never really liked about this figure, although I haven't ever tried to reproduce it, is that it is generally accepted that the breaks in this curve will occur at roughly 1,000 cycles and 1,000,000 cycles. Okay? And it looks like for them, they used a straight line up to somewhere in here. What we're going to do is we're going to use a curve that is essentially like this. It goes to here, and from there down to there. I know it's a small distinction, but it can cause you confusion if you're looking at this and you go, well, they didn't really put it right at 1,000 cycles. All right? So we're going to use 1,000 as that point where it breaks, or not where the specimen breaks, but where the curve has that break point. Okay? And this matters because we're going to have different tools for modeling each segment of this line. Okay? And we sort of skipped over this section because it's not something we use a whole lot, but there's a section where it talks about the strain life method. And in that section, they come up with a formula that, or it's not this exact one, but we can manipulate a little bit and get this one, where the fatigue strength, and it's got a prime on it, meaning that this is again for a highly polished rotating bending specimen. It's going to be equal to this parameter that they call sigma prime sub f. That is called the fatigue strength coefficient. Okay? It's that times 2 times the number of cycles raised to the power of b. All right? And so this is the basic form that we will assume controls the middle portion of this graph. All right? And this middle portion of the graph is what I typically call the high cycle region. So it's above 1,000 cycles when we expect it to fail, but below 1,000,000. All right? The low cycle region occurs over here where it's less than 1,000 cycles. And we have different terms that we're going to come up with for each of these. So here's what we'll do. We are again trying to figure out how do we design for parts when the only piece of data that we've got is the ultimate strength. And so here's where we'll go with that. The first thing that we'll do is we will identify a parameter that we are going to need that describes where this breakpoint occurs. Like, where does this thing actually occur? All right. And the height that I'm identifying right here, we can call that S prime sub F, and I can put in here at 1,000 cycles. All right, another height that we can identify is what is S sub ut. Okay, and that one we don't have to do anything special. It's just S sub ut. So what we're trying to come up with is this parameter that the book just calls F. I think they call it fatigue strength fraction F. F is just the fraction of S prime F at 1,000 cycles. That's, again, just your strength, your fatigue strength at 1,000 cycles. You take the fraction of that value over your ultimate strength value, and that gives you F. And so what you'll see there is that, it might be roughly 80% or something like that, 80 to 90%. And this is going to describe where this thing breaks over. What we need to do is come up with a way that we can come up with what that F fraction is if the only piece of data that we have is ultimate strength. All right? So, it won't be easy, but we're going to do it. So what we'll do here is we'll actually say that your S prime F at 1,000 cycles, which we can actually put that in as sigma F prime, again, that's your fatigue strength coefficient, times 2n. Okay, what is n at 1,000 cycles? Okay. Raised to the b, we don't know what b is yet, but it's going to be of this form. And this is going to be equal to this fraction. Okay, again, that's just the ratio of S prime F over S sub ut times S sub ut. Does that make sense? Right? All we're doing is we're saying this is writing in math what I just said there, that we've got that fraction there. That fraction times ultimate strength should be equal to whatever our value is for fatigue strength at 1,000 cycles. Okay? Well, out of this, we should be able to do something else and actually go ahead and isolate the F. Okay? F just becomes the fatigue strength coefficient over the ultimate strength multiplied by 2 times 1,000 raised to the b. All right. Well, so far so good, but we need to do something to figure out what this value of b is. Okay? And so what we're going to do is turn to another piece of information that is available. This is one of the ones that you'll sort of have to trust me and the textbook that this is something that's out there. But according to the SAE, that's the Society of Automotive Engineers handbook for fatigue, there's a relationship where you can find this fatigue strength coefficient if you know the ultimate strength. And it's going to be the ultimate strength plus 50 KSI. I've never done anything to check that, but that's what they have in the SAE handbook, so we're going to use it. All right? So now what we're saying is we have this value for sigma F prime, this fatigue strength coefficient. All right? What else can we do? Okay, well, another thing we can do is analyze what does this curve do where it hits 1,000,000 cycles, right? So that, by the way, this number, because it's not always exactly 1,000,000, we call that N sub E, kind of means the number of cycles that we're assuming is the endurance number of cycles, okay? So at N sub E, we should be able to write another expression just like the one that we wrote up here, right? So in other words, we should be able to write S, I'm going to make a little break right here. We should be able to write an S sub f prime at 1,000,000 cycles. Or I guess, yeah, so at wherever the location is where you reach this number of cycles, that's your endurance number of cycles. Okay, what would that look like? Sigma f prime, 2 times n sub e, raised to the b. Okay. Now there's another way that we can write this number over here. What's another way we can write that one? We just said that this endurance limit over here is S sub e prime. Okay, so that is that stress value. All right, well, let's see here. I need to make a little bit more room for myself. What that means, if I want to actually solve this thing for B, it means that my B can boil down to the negative log of the fatigue strength coefficient over the endurance limit divided by the log of 2 times that number of endurance cycles. And what you'll see here is that now all of these values are defined. We generally use 1,000,000 for n sub e. Okay? We can find S sub e based on the, that half relationship that I talked about earlier. And our fatigue strength coefficient we can find with our SAE handbook. Okay? So this is basically the process that we have to go through. We have to find B, plug it in to this expression up here, and use that to find F. And we can find it purely as a function of the ultimate strength. Okay? Because it is a single variable, there's only one variable that's controlling this whole method, it is possible for us to just plot the result. Okay? And depending on the level of precision that you're trying to get out of this factor of F, sometimes it's okay for you to just look on here, and if you know the ultimate strength for your material, you can just read what that ultimate strength is, wherever it's at, along here, and go up to the curve and figure out what this fraction F is. Okay, but this whole curve was generated using this technique that I just showed you here. All right, we'll do in our example problem in just a second. I'll show you how to deal with that. Yes, sir. Yeah, that's the notation that they use here in the book, and I just generally try to match it. Ultimate tensile, that's what the UT stands for.
So is that assuming that the compressive strength and the tensile strength are the same?
Yes. All right, we have another couple of interesting, things that we should deal with here as well. One of them is this. What about the low cycle region? Okay, so the thing is at the low cycle region is there is still a relationship between fatigue strength and the number of cycles. Right? And it still is basically given where it's of the form that there is a variable that we need to find A multiplied by n to the B. So whenever you have a log-log curve, straight lines on that log-log set of axes, a straight line on there is going to be of this form. Okay? And so what we need to do for the low cycle region is determine, how do we figure out what A and B are so that we know what our strength is as it pertains to the number of cycles. Okay? Well, as we look at this curve, there's one spot that's really easy for us to deal with. How many cycles right there? 1. Okay? So that tells us here, and the value then of the strength is what? Ultimate strength. So that tells us that S sub ut is going to be equal to A times 1 to the B. Right? So this tells us here that A is equal to S sub ut in the low cycle region. Okay, so that's nice. Where's our other point we should deal with? Okay, we're going to deal with at 1,000 cycles. And now we know that A is S sub ut. And we know that the strength value at this location is going to be F times S sub ut. So F times S sub ut is going to be equal to S sub ut times 1,000 to the B. That allows us to cancel the S sub ut. And this tells us here that B is going to be equal to log base 10 of F over 3. Where's that 3 come from? It's because we had 10 to the third, right? So that's where the 3 comes from in that process. All right, so there's how we deal with the low cycle region. And there's one other thing that I should mention here as well. I mentioned early on that the endurance limit that we've identified on here is if we have a perfectly polished rotating bending specimen at room temperature, and there's a few other things that could kind of control whether or not our endurance limit changes in different ways. We'll get into all those later. What happens once we have evaluated what is called a fully corrected endurance limit? And the answer is this curve actually changes shape somewhat. And you can imagine here that the new curve, after you've identified the fully corrected endurance limit, it's going to end up having an endurance limit maybe that's a little bit lower. Which means this curve actually changes. Right? So what we'll do there is we'll mention again that it is again of the form S sub F is equal to A n to the B. And I won't spend a lot of time deriving these. They're actually not that hard to get to if you need to, but the A that you have here, and again, this is in the high cycle region. The A that you're going to have is going to be F times S sub ut squared over S sub e, and this is not a mistake that I'm leaving the prime off of S sub e. Okay. Whenever we get ready to fully correct our endurance limit, we will no longer put the prime on it. We'll just call it S sub e. Okay, so this is fully corrected. And then B is going to be minus 1/3 log base 10 of F times S sub ut over S sub e. Again, the fully corrected S sub e.
What region is that in?
This is in the high cycle region. And this is basically the first one that we derived just before this was if we have a perfectly polished rotating bending specimen, everything's perfect, right? We had our uncorrected endurance limit. We are going to correct that using a number of factors, which is going to drop its value. And as we do that, if we want to be able to evaluate things like number of cycles in the high cycle region, we have to basically come up with a new value of A and B in order to be able to deal with relating the strength to the number of cycles. We'll do an example here in just a second. I think it'll make it make a little bit more sense. Actually, I think we're actually ready for that example right now. All right, let me explain it a little bit. So what we have here, we have a shaft that is mounted in some bearings. These are ball bearings, and I'm showing the ball bearings, like half of them, so you can see that it's mounted in there. And by the way, this example start I did post on Moodle this morning, in case you want to go back and look at it. Okay. We're saying that this shaft is made out of a polished material, right? So basically, I'm trying to help motivate the idea that I'm not going to deal with any of my correction factors for my endurance limit just yet. Okay. It has an overhang here of 8 inches. The diameter of the shaft is 0.8 inches. The shaft is rotating, and there's a 675-pound flywheel hanging on the end of the shaft right there at an 8-inch overhang. The material is 1141 steel. It has been quenched and tempered at 1,000 degrees Fahrenheit, and it has a polished surface. I mentioned that a second ago. What we want to do is find the number of revolutions that we expect for this thing to last, right, before it breaks the shaft. For part B, I don't want it to break, right? So I want it to last an infinite number of revolutions before it breaks. And so what I want to do is figure out how much would I have to reduce this weight in order to make it last forever. And then for the last part of the problem is, let's say we left the weight alone, and I need to make sure that it lasts 90,000 revolutions. Okay? So these are the 3 parts. And I need to figure out a diameter, a new diameter. Instead of 0.8 inches, I need to figure out a new diameter so that it lasts those 90,000 revolutions. That's my target. All right. Fair enough? What do you want to do first? How about this? We should be able to fairly easily figure out the flexural stress that's at our worst place given what we know about this problem. Is that correct? All right, so I'll do that right over here. Flexural stress, MC over I. Okay, for us, we have what for M? Okay, where's the maximum bending moment going to occur? I think you might be saying right here. Yeah, this is where your critical location is going to be. All right, so we need to take the amount of weight we have hanging off the end and multiply by 8 inches. All right, C is what? Yeah, so C is basically the radius of the shaft, and we'll have to take the 0.8 inches, divide it by 2 to get the radius. Okay, and what about I? pi over 64 times 0.8 inches to the fourth. Okay, and if we punch these in, the stress that we calculate is 107.43 KSI. All right, I'll tell you what we need to do now is we need some data about this material. Is this a lot or is this not a lot relative to the strength of our material? All right. I will tell you that this is in table A21. It's right at the bottom of the page. This material that's tempered at 1,000 degrees Fahrenheit has an ultimate strength value of 130 KSI. All right. And just kind of as a matter of interest, let me figure out my yield strength value as well. It says it's 111 KSI. So we're right close to yielding it, but not quite. All right? This is actually one of the things that we check for sometimes in these fatigue problems is we sometimes check for first cycle yielding. In other words, before you even start cycling it, is it just going to make the thing yield? All right, so what we're saying here is that it looks like we're fairly safe on first cycle yielding. We are likely, though, if we think about the 130 KSI, if we have S sub UT, let's actually go up and look at our chart for just a second. Okay, 130 KSI puts us right here. All right, looks to me like that's a little bit above the midpoint. And so let's say that that's about 0.81. We'll figure it out exactly in just a second. So that's about 0.81-ish. Do you think we're in the low cycle region or high cycle region? Let's figure it out exactly, okay? We don't need to guess. That'll be the next thing we do, is we have to run through this technique that I just set up here. All right? So the first step that we will do, I guess, is we will figure out the fatigue strength coefficient. It's 130 KSI plus 50 KSI. All right. The next thing we'll do is figure out S sub E prime. Right? That's our uncorrected endurance limit. It's going to be equal to 0.5 times what? 130 KSI. And that gives us what? 65 KSI. All right. Then what do we do? Okay, we can figure out what that exponent is, B. B is going to be equal to minus log base 10 of sigma F prime. Okay, so that's 180 KSI over S sub E prime. This is over log base 10 of 2 times a million. Okay, and I think I might have sort of mentioned it, but I'll just say, if you're not given information about what you're supposed to use as the basis for where you assume it is infinite, use 1,000,000. If you're told something else, use something else. But if you're not told, just use 1,000,000. Okay? All right. And so what this gives us is a B value of negative 0.0702. All right, then the last step is our formula for F. F ends up being our fatigue strength coefficient. Tell you what, I'll just put that in there, 180 KSI over S sub UT, 65 KSI, multiplied by 2 times 1,000, raised to the negative 0.0702. Yes, sir. The formula that I'm going to is up here. Oh, S sub UT. Thank you. Yeah. You are correct. I put in S sub E prime, and the formula actually calls for S sub UT. Good catch, Tom. I have it correct in my notes here. I just wrote it wrong. So, all right. So that means that I end up with an F value of 0.81205. Okay. Which tells me that my break point from being low cycle to high cycle, okay, so this is basically that S sub F prime at 1,000 cycles. This ends up being 0.81205 times 130 KSI. All right. I forgot to actually do that particular calculation. 0.81205 times 130. So 105.6 or so. Now what we want to do is look at the relative value between these two. The actual stress we're putting on it is 107.43 KSI. The amount of stress where we break from being low cycle to high cycle is at 105.6 KSI. Which one is higher? The stress we're actually applying, which means that if we go up and look at this chart, we're above this little knee in the curve, which means we're up here in the low cycle region. Okay, so that means we want to use these low cycle formulas. All right. So the high cycle region happens at lower stresses. Right? So we're above that stress level, which means we're up here in this range of the curve. Okay. So we'll go down here and use these formulas. Okay. What is A? What is B? Okay. Okay, and so then that means that our strength value, S sub F, is going to be equal to 130 KSI times N. That's what we're going to try to solve for, raised to the B of log of F over 3. Okay. What do I do with this? This is a strength value I can set equal to something else, right? So instead of saying that is my strength value right there, but instead of setting that as just saying that's the strength value, this, if that's the actual stress value that we're applying, right, and we have that number, that is the 107.43 KSI. And by the way, get comfortable using your calculator for this. I won't spend a lot of time on it right now, but you can use your Casio or your TI calculators with this. Just be a little bit careful because it is kind of sensitive to what your initial guess is. So worthwhile practicing a little bit. Make sure that you're comfortable using it for that purpose. The N that comes out of here is 559.6. Revolutions. Do we know it that accurately? Do I know that in 559, it's not 560, it's 559.6? Being a little bit facetious. No, we do not know that, right? We're making a guess. Yeah, it gives us an idea, okay? But it's, you know, it's worth doing in some cases so that you have some ballpark idea of how many cycles it might run. All right. What's our next step? Okay, now we got to say, oh, right, or we don't want to do that. Let's see how much do we have to reduce the weight by in order to make sure that we are not going to ever fail. Okay. What's our step for that, you think? Okay. We had all this stuff, but what we're going to do is change and say instead of 675 pounds, right, we're going to make that a variable and call that F. And what do we set all this equal to? Say what? Okay. If we want it to never fail, then we want to make sure we're not going above our endurance limit. And right now we're not thinking about trying to adjust our endurance limit at all. We're just going to use the same one as we would predict for a fully polished rotating bending specimen. So we just put in a 65 KSI. Okay. And if you solve now for F, you say don't put any more than 408.4 pounds. And then you would predict that it would last forever, assuming that you don't need to do any more adjustment on S sub E. And assuming you're not trying to apply a factor of safety, and assuming, you know, there's a few assumptions there, but that's like you're right at the threshold. Okay? What's our last question that we asked? Find a diameter so that with the 675 pound weight, we would predict a lifespan of 90,000 revolutions. Okay? So what equations would we need if we're wanting 90,000 revolutions? Okay, we want our high cycle numbers. And at this point, we are not making a distinction for this exact problem between fully corrected and uncorrected, right? So what we can do here is we can say that 675 pounds times 8 inches times d over 2, correct? Over pi over 64 times d to the 4th. We're saying this is going to be equal to A, which is F, 0.81205, times S sub ut, squared over, like I said a second ago, S sub e and S sub e prime at this point are not different, but they will become different at some point in later problems that we work. All right, that was 65 KSI. All right, this is multiplied by N, 90,000, raised to the minus 1/3 of what? Okay, we're over here. Minus 1/3 log of F times S sub ut. We're going to run out of space over here, aren't we? 81205 times 130 KSI, and that was over S sub e, which is 65 KSI. And solve for D. The D that makes this happen is 0.894 inches. So if you wanted the diameter, if you want to be able to hold the 675 pounds and you want the diameter that helps you do that, what's the procedure for doing that?
Use the low cycle formula.
Yeah, so instead of figuring out S sub F at 90,000 cycles, which is what I did in that right part of that equation, you just plug in your endurance limit and solve for D. It ends up being a little bit more. All righty. Anyone have questions? All right.